So we are solving an equation where we were given to be, where we were given an equation, a differential equation like this. This equals minus y dx plus x dy. And if we solve minus m partial m over partial y and partial m over partial x, it comes out to be minus 1, and this is 1. So partial m over partial y isn't equal to partial n over partial x. This means it's not an exact ODE. So what we should do is we should introduce an integrating factor f. That is, let's guess the integrating factor to be x squared. So this is my guess, your guess can be different, and shortly you will see how can we mathematically find this integrating factor, and then it will no longer be a guess. So this is minus y over x squared dx, right? So plus this is 1 over x dy, and if we now compute partial m over partial y and partial n over partial x, they both come out to be minus 1 over x squared. You can check. So now partial m over partial y, since it is equal to partial n over partial x, the new equation is indeed exact. So what we are going to do is we are going to find this new equation. This new equation is of course exact. So now we are going to find out the solution. So u will be m dx, integrated of m dx plus ky. So u is minus y over x squared. M is minus y over x squared now, dx plus some constant. So if we integrate this, it comes out to be minus y is a constant of integration. So this is x to the minus 2 dx plus this ky. So it becomes x to the minus 2 plus 1 minus 1. So minus x to the minus 1 plus ky. So this is y over x. This comes out to be y over x plus k of y. So this is u, and the solution after we have converted this given equation to exact, and it wasn't initially exact. Right, so now we are ready to find the solution and find the value of k of y. You know, partial u over partial y is n. Partial u over partial y would be 1 over x plus partial k over partial y, and we know that in our new equation n was also 1 over x. So in our new equation we computed n to be 1 over x. So this 1 over x cancels with this 1 over x, and partial k over partial y is equal to 1, or k can be equal to y plus some constant of integration c. So now we can complete this u by replacing this k of y with this y plus c static, and we know that for all exact type of differential equation, the solution is equal to some constant. Let's call it k. So we can write it y over x plus y is equal to k minus c static, and let's call it c. So the solution is y over x plus y is equal to some constant c, and this is a general solution. We cannot find a particular solution because we don't know the initial conditions. So up till now we have studied that given an equation that looks to be an exact equation but actually it is not, how can we find its solution? So that's how we can multiply with an integrating factor f and then we can solve and we can check that whether this new equation is an exact, and if it is, we find the solution like we do for exact type of equations, right? So now the question is that we studied that if up till now we have studied that if we are given m dx plus n dy is equal to 0 and partial m over partial y and isn't equal to partial x, the condition isn't fulfilled, we can multiply both sides by an integrating factor f, and then we can check that partial m partial y is equal to partial fn over partial x. If it is, we can solve it like we do it for an exact type of ODE. So this is the concept. The question is how to find. Now the question is how to find the integrating factor f mathematically. How to find the integrating factor f of x mathematically. So we have to apply some check. We have to first compute the residual. That is r is 1 over n partial m over partial y minus partial n over partial x. So we first compute this r, the residual, and of course this whole thing can be proved and it is given in the book. And if r is a function of rx, that's simple. If this residue comes out to be the function of x only, f is e to the integral r dx, but this f is only equal to this if we have r, the residue, that comes out to be only the function of x. But else if r is exactly equal to the function of x only, if it is a function of x only, the integrating factor would be e to the integral r dx. Else, if it isn't function of x, we have to compute its counterpart, its brother, its sister. Partial n over partial x minus partial m over partial y. So we'll replace the position of these two ratios, and instead of multiplying with 1 over n, now we multiply with 1 over m. And now the solution would be e to the integral r static dy. So this is the whole algorithm, this is the whole procedure to compute the value of integrating factor for a given ODE to make it exact. If it isn't exact and you want to make it exact, you will follow these steps. You're given an equation, you find that it is not exact, you apply the check, partial m or partial y and partial or partial x, they don't come out to be equal. You say, okay, it's not exact, let's compute its residual, and once you compute this residual, then you can apply two checks. If its residual comes out to be only the function of x, this would be your solution. Otherwise, it would be you would compute the counterpart of r static, and that counterpart would be used to compute this f now. So the steps would be the first, given an ODE, the steps are we need to first compute. We need to first check whether this is an exact type of ODE or not. So given this equation, ODE, the ordinary differential equation, this one plus e to the y minus 1 d5 is equal to 0. And of course, we are also given the initial condition that pi of 0 is a 1. Oh, not 1, minus 1. Y of 0 is given to be minus 1. So first we have to check whether this is an exact type of ODE or it is not. So partial m over partial y is e to the, if we integrate this, if we differentiate this with respect to y, this is e to the x plus y times the derivative of x plus y, which comes out to be 1, plus y, the integral of the derivative of the second term e to the y, the product rule, y e to the y plus the derivative of y, which is 1, and e to the y as such. So this is how we use this this product rule in our school and colleges, that if we have two functions of your variable y and they're multiplying they're being multiplied with each other, and you take the derivative, you want to compute the derivative of this y e to the y, you compute the derivative of the first dy over y, and you write first as such, and you compute the derivative of the second, plus you compute the derivative of the first, and you keep the second as such. So this is y, derivative of e to the y is e to the y plus derivative of y this way to y is a 1 times e to the y, So this is what we reach to. So we reach to this solution. Okay, so partial m or partial y comes out to be this. Let's see what partial n or partial x is to check the necessity and sufficient condition for this given equation, for which someone has claimed that it's an exact, and we are going to check whether it really is an exact type of equation. So partial and partial x, e to the y is a constant, and x is the derivative of x with respect to 1 minus 0. So it comes out to be e to the y. So here partial m or partial y isn't equal to partial n over partial x, because partial n or partial y is this long statement. Partial n or partial x is only e to the y. So they aren't equal, it's not exact. So what we're going to do next is we are going to have a proper f. Either we have this f, we'll have this f, or we'll have this f. But to find the integrating factor f, you have to find the residual term first, r. You have to find r first. So the residual term r is 1 over n partial m or partial y minus partial n over partial x. So we have already computed partial m or partial n, partial n or partial x, so we can compute r straight away. R is 1 over n is x, e to the y minus 1, partial m over partial m over partial y, this is e to the x plus y e to the y plus e to the y minus partial n over partial x is e to the y. And this e to the y minus e to the y, they cancel each other. But still, this r isn't, even after cancelling these two terms, r isn't r of x. R is not the function of x. So next what I am doing, this test fails. For this equation, this test fails. So we have to apply this second test. And that would be to compute r static. And that is 1 over, instead of 1 over n, now we have 1 over m. This is e to the x plus y e to the y. have partial n over partial x minus partial m over partial y. So partial n over partial x is e to the y minus e to the x plus y minus e to the y minus e to the y. So this e to the y cancels with this e to the y, and we are left with minus e to the x plus y. Right, so if we take this minus common, the numerator is e to the x plus y e to the y, and the numerator and the denominator is e to the x plus y e to the y. So they two cancel, and our static comes out to be minus 1. So now we're going to compute f, which is e to the integral of r static. So f is the integrating factor. So now we are going to compute the integrating factor. F is integral r static minus 1 dy. This one, we'll use this because this test has failed. So this is e to the minus y, right? So f comes out to be e to the minus y. E to the minus y is the integrating factor that if we multiply it on both sides of the equation is reduced to an exact type of ODE, and then we can use the normal way to use the normal method to compute its solution. So e to the minus y. E to the minus y is our integrating factor. So let's apply this integrating factor and solve this equation. Let's apply this integrating factor. Now we are very close to the solution. E to the minus y. So f comes out to be e to the minus y. So we are supposed to multiply e to the minus y, the f, on both sides of the equation. E to the minus y. So if you multiply e to the minus y to the x plus y minus y, so it is reduced to e to the x plus y e to the y minus e to the y. E to the y multiplied by e to the y. So e to the y multiplied by e to the minus y is e to the y minus y is e to the 0, it's of 1. So this is how it is. So multiplying e to the minus y with e to the y, it comes out to be a 1. So this is y, and this whole times dx plus e to the minus y. So x e to the y times e to the minus y is a 1. So we are left with only this x, and this minus 1 times e to the minus y is minus 1 dy. So this is our new equation. Let's forget everything, and this is our new equation. Let's forget everything else after we have multiplied this with an f. This is our new equation. E to the x and dx plus x minus e to the minus y dy. And we are pretty confident that this is an exact type of equation, but still we can check. We can check it. So how would we check this? Partial m over partial y is partial over partial y e to the x plus y. So e to the x is a constant, so its derivative would be 0 and the derivative would be 1. And partial n over partial x is partial over partial x minus e to the minus y. So the minus y is a constant, so partial over partial, so x is 1. So that's straight. It's partial m over partial y. For this new equation, it comes out to be partial n over partial x, and it's now exact. It's now exact. That's the great news, that it is exact now. So what would be the solution? Now we are very close to the solution. The solution, we know this, there are two possible solutions. There are two possible solutions. Either it is u is equal to m dx plus k of y. Either we can use this solution or we can use this integral n dy plus L of x. So m is e to the x plus y so I have to integrate this with respect to x. So this is y times x plus e to the x. Integral of e to the x is e to the x plus k of y. So this is u. Right. So we have computed the solution, but we are only left with this k of y, and for that, of course, we know that we always computed using this partial derivative partial u over partial y, which should be equal to n. So we use this to find this unknown k of y. We always do this. You already know this. Partial u over partial y. We put it equal to n. We know that it is equal to n. So partial u is given. Partial u over partial y is x times y. So x plus 0, because it's not function of y, plus partial k over partial y. And this n comes out to be x minus e to the minus y. So this x cancels with this x, but partial k over partial y. It comes out to be minus e to the minus y, or right. So if you integrate on both sides, partial k integrate with respect to y is minus e to the minus y dy, and if integrate 2, this comes out to be minus, and the integral of e to the minus y is e to the minus y over minus 1. So this is e to the minus y plus some constant of integration, c static. So k comes out to be e to the minus y e to the minus y plus some constant c static is equal to some constant k, because we know that this u is equal to k. This u is always equal to some constant. So taking this c static on the other side, k minus c static can be written with, they can be written as another constant. Let's call it c. So this is our solution. E y times x plus e to the x plus e to the minus y is equal to c. This is the solution. So finally, after doing all the tricks, finding this integrating factor and then checking whether it is exact, and then finding out that it is really exact, now we have computed the solution u, and then the constant, then the other function k of y. So now we are done. We have this, but it's a general solution, we know. It's a general solution. And we can make it particular solution because we are also given the initial conditions. Y of 0 is equal to 1. Y of 0 is equal to minus 1. This means that if x is 0, y is minus 1. So let's put x equal to 0 and y is equal to minus 1 in this solution to find out the value of this constant c, constants of integration. So this is minus 1 times x. X is 0 plus e to the x, e to the 0, plus e to the minus y minus into minus 1. It's a constant c. So this comes out to be c. This is 1. This e to the 0 is of 1. So 1 plus e to the minus 1 times minus 1 is e. This is equal to c. So c is e plus 1. E plus 1. We know e is 2.71828 plus 1 is 3.718. So c comes out to be 3.718. So now we can plug these values of c into the solution to find out the particular solution. C is 3.718. So the particular solution is for this problem is now y times x or x times y. It's your choice. E to the x plus e to the minus y is equal to 3.718. So this is the solution, and of course you can plot it. Right, so that's all for this lecture. In the next lecture we will study linear ODEs. In the next lecture we will study linear ODEs, and we'll solve some examples from linear electrical circuits. Right. Thank you.